Today we have Michal Doucha, who will talk about the structure of unitary groups on C-star algebras. So take it away.
But on the other hand, maybe we are not sure where we are exactly heading. Maybe
it sounds very faint, but it might
I can see the, when you talk, it's not green.
Yeah, so I just wanted to say that everything is very far from the environment, but on the other hand, maybe it's a good opportunity to talk about it, because maybe if you have some comments, it will help us to have some idea of where we can go. But also, it's the first time I tried to yesterday and today I tried to organize the results that we have produced so far, and because of this, I mean, many of the things that I thought were fine actually were some flaws and gaps. So many of the statements that of the result I will present are literally a few hours old, different than they were yesterday. So I hope that I will not get into troubles and won't get stuck and test them not for too long. Okay, so maybe let me just say some historical motivation. So we started looking with Hiroshi at these unitary groups a few years ago. I mean, we are studying some paper of Chris Phillips and Ring Rhodes and some other people. And I mean, our motivation was to study the large-scale geometry of these groups, because these people essentially they were doing their language something else, but in our language, essentially they were doing large-scale geometry groups. And one of the main things they used was the Lie theory of these groups. But at the end, we noticed that what they did for be generalized to more general Lie groups. So at the end, we left unitary groups and we wrote together a paper on in general on large-scale geometry of Banach groups. And this time we had to back again to unitary group, and we wanted to somehow explore this possibility to investigate these groups theoretically more, but like from a different perspective, which nothing else. And this time we are focused more on the structure, like the normal subgroup structure, and so on. And I should say that it seems that this Lie group structure of unitary groups is not so well understood or exploited, because, for example, in this paper. Okay. Yeah, so it's worse than was before, no? Yeah, so apparently they, for example, these papers of Chris Phillips or Ring Rhodes that I mentioned, they were apparently not aware that unitary groups are Banach Lie groups, because they were reproving some very general facts about Lie groups, like total product formula or Baker-Campbell-Hauser formula for these groups again. On the other hand, they were proving something which could be generalized to general Banach Lie groups about their geometry, so that was nice. But this time our motivation is a paper of Leonel Robert, where he explicitly used the fact that the unitary groups are Banach Lie groups, and with this he was able to answer some question of Elliott and Rodham about simplicity of these unitary groups, which is something which Elliott and Rodham proved for some very specific C-cell algebras, and Robert could use it, could prove it for general C-cell algebra by these Lie theoretic methods. Yeah, so let me start with some just basics of linear Banach Lie groups. So, like in general, when you want to introduce standard finite dimensional Lie groups, maybe you start with matrix groups. So in the same spirit, let me just introduce what can be called linear Banach Lie groups. So this the starting point is that we have some Banach algebra. And then we look at the group of invertible elements. So this is group of invertible elements. And so it is a Banach Lie group. So what does it mean? So there is a Lie algebra for this group. This is this whole Banach algebra A. And the main tool how to relate the Lie algebra structure of A with this group of invertible elements is like in the matrix case the exponential function. So we have the exponential function going from here to here, which is defined like in the standard matrix case by this series. So this is something which converges in every Banach algebra. So it is a well-defined function, and the fact that this is a Lie group is that the exponential function is a local homeomorphism. Actually, it is a local diffeomorphism, but this will not be so useful for us. But the fact is that there is some open set containing the zero, so that the exponential function restricted from this open set is a local homeomorphism, or just homeomorphism. And then another fact is that there is this binary function, binary relation from A to A, which if you take x and y from A, so this is this relation which defines which results from the Baker-Campbell-Hauser formula. So this is something which is defined in this way, like x plus y, then plus the commutator of xy, and then there are some other terms. So I don't know, from 3. And each of these terms is just some higher forms of of commutators. And this relation has the property that if you take any x and y from A, then it relates to the standard addition. Sorry, I should use. I should say that, and also from, let's say, from this open neighborhood, that the exponential of x star with I is is the product of the exponentials. And what I wanted to say before is that the addition is related to this formula by this equality, by this limit. And just from this, we derive this thing that I mentioned, this total product formula, which is something that we'll be using all the time in most of the proofs. So from this, we derive that the exponential of x plus y is equal to the limit of n going to infinity of exponential of x over n times exponential of y over n, and the whole thing power to n.
Are you saying that whenever you have done an algebra, and you look at this, it satisfies the problems, or?
Yeah.
Okay.
Yeah. Yeah, and here we don't need to take x and y from this neighborhood, because eventually, because here n is growing to infinity, eventually it will end up there. And what else? Yeah, so also one basic fact which follows from the fact that the exponential is a local homomorphism is that every g from the group of invertible elements is a product of exponentials. So that there exists some a1 up to an, so that g is equal to g is equal to product of these exponentials. But then in general, we want to work with subgroups of this group of invertible elements. In particular, when n is a C-star algebra, we want to work with the unitary group, not with the whole group of invertible elements. So maybe we need also the notion of a Lie subgroup. So sorry, yeah, here I should say for every g from GL0 of A, which is the connected component of the identity. Yeah, yeah, this group of invertible elements doesn't have to be connected in general. Yeah, so closed connected subgroup G of GLA is a Lie subgroup. So if there is some Lie subalgebra, so if there is some I cannot work with these chalks. I don't know why.
There's a big square one. In the other.
Sorry?
And then I need a big square one. Big better.
No. So Lie subalgebra, meaning it is a closed linear subspace which is closed under the commutator relation, and with the property that that the exponential of this open neighborhood U, which is fixed, intersection with this G is the same exponential of what? Of U, intersection with G. So this actually implies that the G itself is a Banachly subgroup. Yeah, so let's now work finally with the unitary groups. So if A is a unitary Caesar algebra by U of A, I will denote the unitary group, and I will denote by UA with A lower index the connected component of the identity. So yeah, so this is a Banachly subgroup, and also we will work. And so naturally the Lie algebra of this would be the set of all skew adjoint elements, but we will actually work with something isomorphic. So for us, the algebra of UA will be the set of self-adjoint elements. So it is not really it is not strictly speaking the Lie algebra with the standard exponential function. So in this case, we need to replace the exponential function by exponential with the imaginary, meaning that if A is self-adjoint, then the exponential of I times A is in the unitary group, and the same the brackets. So the brackets here must be replaced by I times the standard brackets to have the result again self-adjoint. Yeah, so the first thing I want to consider is the normal subgroup structure of this group. So and how it is related to the ideal structure of the algebra. So I will introduce a few more subgroups. So whenever we have a ideal I of A, I mean always close to sided ideal, then UI will be defined as those unitaries from UA such that G minus 1 is in I. And there will be two more important subgroups. So one will be the commutator subgroup. So C of I will be defined as the closed commutator subgroup. So this is the closure of the subgroup generated by all commutators. So closure, yes. Yeah, so these groups are Lie groups with respect to the norm topology. Yeah, I is any close to sided ideal. Yeah. And then we have one more important group that we consider, and this is the group of those elements from UA such that if you take the commutator of G with anything from UA, it will be inside Yeah.
The commutator is the
yeah, sorry. So this is the multiplicative commutator. So this is G U.
So when you write round brackets, does that mean multiplicative or that's?
Yeah, round brackets is the multiplicative commutator. Yeah. Yeah. So Ni is defined as those unitaries from the quantitative component oriented that whenever you take a commutator of G with anything from UA, it will be in the unitization of the ideal. So this is by this I mean the unitization. And actually, it is the same, which I will not prove, as those elements from UA such that this commutator is inside this CUI. Yeah. So what Robert proved in his paper is that that this, by which I mean the closed linear span of commutators from I, that the exponentials of elements from this generate this CUI. But it is not in general. So we actually don't know if this is a lead subgroup. We guess that it is, but we don't have a proof. But definitely this. So this is some lead subalgebra whose exponentials generate this commutator subgroup, but it is not in general the Lie algebra of this. So it can happen that, for example, that we have that the whole A is a direct sum like this. However, this CUI is actually equal to UA. So it means that this proper subalgebra of I should write self-adjoint. Well, let's keep it like this. So the self-adjoint elements from this cannot be the Lie algebra of this. On the other hand, we know that this Ni is a Lie group. And its Lie algebra is those elements, let's say self-adjoint, such that these commutators are inside this. Yeah, so actually I wanted to prove it, but because I'm going much slower than I expected, maybe I will skip it for now. And let me just describe the yeah. Well, so there are many comments. So what?
The first five ones, the other ones are just like block questions.
Also, the last one depends what you mean. There are Banach Lie algebras which are not Lie algebras. Yes. Yes. But so how? Yes, there are Lie algebras which are Banach Lie algebras which are not Lie algebras of any group, but now I'm confused. How is it related to what I said? Yeah, I was saying that that this CUI. So we don't know if it is a Lie group or not. It has a. We just know that this Lie algebra is in general not Lie algebra of this. I mean, you can define Lie algebra of any closed subgroup, even if it is not a Lie group. But we know that in general, this is not the Lie algebra of this.
So you're saying any Banach algebra is otherwise a thing. I thought that was the definition of Banach Lie. What's the definition of Banach Lie?
Okay, Banach Lie algebra. Well, okay, either you can have a completely abstract definition, or in this linear case, it will be just a linear subspace of a Banach algebra which is closed under the commutator operation. But it. Yeah, but I mean, you can not from every Banach Lie subalgebra you can get a Banach Lie group. I mean, not every Banach Lie subalgebra is a Lie subalgebra of some Banach Lie group. Definition of Banach Lie group. Well, so let's say for Banach Lie subgroup, it is. Yeah, so it is something for which there is a Banach Lie subalgebra. So for it's a let's say as a connected subgroup of this, for which sorry, okay, that's confusing. For which yeah, for which there is a Lie subalgebra satisfying this. Yeah, so actually, if you have any closed subgroup, you can define the subalgebra like the set of those elements from A, such that the exponential T(A) is in G for every, let's say, real T. This will be a Banach Lie subalgebra for any closed subgroup. But we need this additional condition. The exponential of U. So U was this special open neighborhood where exponential function is a homomorphism, and the intersection with this Lie subalgebra is the same as the intersection of exponential of this neighborhood intersection with the group G.
Okay, saying in general you might get like a proper inclusion.
Yeah. Yeah, so I will not prove this. Yeah.
Which is a relatively easy one. What is the tilde on I in your definition of ni tilde ni?
Yes. Yeah. So what Robert proved is that whenever H is a normal subgroup, then there is an ideal. Actually, the ideal is explicitly defined. It is defined as the ideal generated by these commutators, such that H is in between these. In between these two groups. Yeah, so he proved something slightly weaker, but actually it is, yeah, it is essential. It is essentially this. So so let me just add some extension to this, which we did. Maybe first let me start with a definition. So let I be an ideal and say that it is perfect if you take I prime, which is by definition the ideal generated by the commutators from A, it is actually equal to, it is equal to I. Yeah, so our contribution here is that, so there are several points. So first, for every ideal, this I prime defined like this is perfect. Second, the ideal defined by Robert in this way from some normal subgroup. So ideal of this form is perfect. Yeah, so then what we get from this and the combination of Robert's result is that all normal subgroups of the unitary group lie between are exactly the subgroups that are in between these two groups where I is perfect. Yeah, so one direction, if H is a normal subgroup, you get that it is in between these two groups. But actually, the additional information is that that I is perfect. And conversely, when you have I perfect and you take anything between here, then it is actually normal. And for different perfect ideals, I mean these lattices of subgroups are disjoint, different. Yeah, so I will.
So not sure if I can say something. Can one hear me?
Yes.
Great. So does perfect not just exactly mean that there's no one-dimensional representation of the ideal? So it has no character?
Yeah, I don't know. I would have to think about it. I don't know.
I think so. I mean, it's an obvious obstruction, right? I mean, if you have a one-dimensional representation, then under that representation, all commutators vanish. So that the ideal generated by commutators is definitely in the kernel of this character, but it's also the other way around. I mean, so, and I think it's kind of in Robert's paper.
In Robert's paper?
Maybe not explicitly, but it's somehow, you can pull it out. Yeah.
Yeah, so for example, when you want to find an example of an ideal which is not perfect, I mean, you can take, if you have A which has some abelian quotient, so that this is abelian, then it means that that is I is in between. So so I itself is not a perfect ideal. Yeah, so this is kind of related, right? Because then you have one-dimensional representation.
Yeah, right.
Yeah. Yeah. So yeah. So let me maybe hurry a bit. So I want to go to something next, and now I want to apply this to a characterization of normal subgroups of the group of approximately inner automorphisms. So let me denote by VA the subgroup of approximately inner automorphisms, but which are generated by unitaries from the connected component of the identity. So let me just yeah, so this will be by definition the closure of this inside the group of automorphisms of A, but where the unitaries are just from the connected component of the identity. And we want to characterize all the normal subgroups of this group. So again, if I is an ideal, then we can define normal subgroup like this. So generated by these unitaries where U is from UI. So this is a normal subgroup of VI, and our result is that actually this let's denote this map phi, which associates an ideal to a subgroup VI. This is a one-to-one correspondence between not all ideals, but between perfect ideals, between perfect ideals and closed normal subgroups. Yeah, so I will try to prove it, or at least sketch the proof. So first, that this map phi is injective. So let's have two perfect ideals, I and J. And suppose that VI is equal to VJ. So then we have that this ideal that I will denote I hat, which is by definition an ideal generated by these elements. So you take any U from UI and any X from A, and you look at the difference of X and where edu of x moved it, and to generate an ideal by this. So this is obviously equal to the ideal generated by phi of x minus x, where phi is in vi and x is in a. Now this is equal to the ideal generated by phi of x minus x, where phi is from vj, because our assumption is that vi is equal to vj. And this is equal, I mean, with some manipulation that I will omit for now, that this is equal to the ideal generated by the commutators from ui and a, and this is further equal to I prime, which is the ideal generated by commutators from a. This is again some small manipulation that I will omit, and this is here very analogous. This is equal to j prime. And here on the left side also we have something analogous like here. Which by definition is j hat. So by the equality between these two, which is by definition, we also get that I hat is equal to j hat. And then because I is perfect, I prime is equal to I, and j prime is equal to j. So in total, we get that these two ideals are equal. So now let me prove that that this map phi is on 2. Yeah, so let H be a closed normal subgroup. Closed normal subgroup. So we look at the unitaries whose image is inside this H. So HU is the set of those unitaries such that at G is inside H. So because this adjoint map is a continuous homomorphism with a dense image, this HU is actually a closed normal subgroup of UA. So by the previous discussion, we get some perfect ideal I perfect such that HU is in between CUI and NI. And now the claim that we want to prove is that H is equal to VI. And how we prove it? So we prove that the closure of the image of this CUI is equal to the closure of the image of NI. So in particular, it is equal to the closure of the image of anything in between, so also of HU. So the argument is, so actually I should say that, so Robert proves that this equality is true for CUI and here for UI. And we prove that it is true also when we put here this bigger ni. So what we need to do, we need to approximate. So we take any big some u from ni, and we need to approximate add u by unitaries from CUI. And here is the point where we use that that Ni is a Banachly group, which is what I wanted to prove. So we have that actually U is equal to the product of some exponentials, where each Aj is from, I hope it is still somewhere on the board. Yeah, where each A is from this set. So it's the algebra of Ni. Yeah, so let me just, I will suppose that for simplicity, suppose that U is just one exponential. And also suppose that for simplicity that A is separable. And so we continue somehow similar like Robert. So there is a result of Kirchberg and Rodam, who says that for every finite subset f of A, and for every epsilon, there are finitely many unitaries W1, Wn from UA, so that this element Wj A Wj star, where A is this fixed A, that this epsilon commutes with everything from F. So if you take a commutator of any element from F with this element, then the norm will be less than epsilon. So we will so let's set Bn will be an element of this form, so it will be 1 over say, some m with the property that so that there is some sequence of finite subsets of A and some epsilons, so that these epsilons go to 0. The union of these fn's is dense inside A. And we have that A minus Bn epsilon n commutes with Fn. Yeah, so here is the. Yeah, so now in order to somehow move from some epsilon data analysis into something softer, I mean, we will work in, let's say, in some ultra power of U. So U is some ultra power of U where A is inside by the diagonal embedding, and we denote by B the element inside the ultra power, which is defined by the sequence of these B ends. And then we have that A minus B inside this ultra power commutes with A, right? Because these elements epsilon n commuted with elements from Fn, and epsilon n's were going to 0. So inside the ultra power, this literally commutes with everything from A. In particular, it commutes with A itself, which implies that also that A commutes with B. So inside the ultra power, we have that the exponential of IA minus B is equal to the exponential of IA times the exponential of minus IB. And yeah, so now going back to the original algebra, we can get that if we take so from this it follows that if we take any finite subset F of A and any epsilon, then we can find some n such that A minus Bn exp IA exp minus I Bn epsilon commutes with F. All right, so because A minus B commutes with everything from A, also their exponential commutes with everything from A. So then when you go back to the original algebra, if you take any finite F and an epsilon, you can find a big enough n so that these two exponentials epsilon commutes with everything from F. But this means that the norm of exp IA times exp minus I Bn x, where x is something from F, minus yeah, so you know what here is. I just want to be a bit faster. This is equal to at Bn x minus at A X. And this is less than epsilon. So this automorphism induced by this unitary A is approximated by the unitaries Bn. So we just need to show that the exponential of each Bn is inside CUI. But so Bn, I'm very slow. Bn is Bn is of this form here. By the third product formula, you get. Yeah. So let me just show for simplicity that the exponential of let's say W star minus A, that this is inside CUA. I mean, the general form of Bn is some sum of this, but then you again use third product formula to make everything work. So this is by the third product formula. Third product formula. Yeah, this is something. Yeah, it was somewhere on the. Yeah, it follows from this. Yeah, so it was. Yeah, so actually, so let me define it again here. So this is the limit of n going to the infinity of x A over n, the commutator with u, and the whole thing the power to n. But because A by definition was in the Lie algebra of Ni, this thing is in the group big Ni. So by definition, this is in Ni. So the whole limit is inside. Sorry. This thing is in Ni. So the commutator is by definition of Ni inside CUI. Yeah. So by applying the same formula also for the sum of these things, you get that this whole thing is inside CUI. And this is the end of the proof. Yeah, so I have yes, less than 5 minutes. So yeah, so this so now we prove the surjectivity. We prove that this map is on 2. Sorry. Yeah, I guess. Yeah, because yeah, I mean it's defined very explicitly. So yeah. Yeah. So in the last, so maybe I will just formulate the results that I wanted to prove, but I mean I was very naive, thinking that I could really prove it. It has to be what?
It has to be allowed to play with it. I understand you've got an order of these normal subgroups and these
His perfect deals. Yeah.
If one ideal is better than the other, then the correspondence.
Yeah. Yeah, so one thing what I wanted to prove, which was, I mean, kind of interesting for us, but I don't know. So that whenever we have, so we were considering groups which were normal inside this connected component of the identity. But so what we can prove that if H is so normal, but moreover it is Lie, then actually H is normal even inside the bigger group. I mean the whole unitary group. I mean, which is something which I don't see a reason why it should be true. I don't know if it is some more general theoretic result, but in this case we can prove it. It is normal inside the whole unitary group. And just some, I mean, funny consequence. I don't know how useful it is that if you have a subalgebra which is at UA invariant, so invariant under all unitaries from the connected component of the identity, then it is automatically invariant under the unitaries from the whole unitary group, because you apply this thing to H being the unitary group of B. And one more thing I wanted to state, proof actually. Yeah, then also I wanted to mention that all these things, so we proved it for groups which are normal inside U of A, but also we can prove it for that they are invariant under any subgroup of the automorphism on the whole automorphism group of A, which contains all the unitaries. So if you have any G which is between out of A and in between the approximately inner automorphisms, then we can have some characterization of those subgroups of UA which are G invariant. And then the last thing I wanted to prove that so let's assume that A is again unital C-star algebra, and suppose that has at most one trace. And maybe I'm not sure if it is relevant, but just to be safe, maybe let's assume that it is not equal to the complex numbers. Then we have that A is simple. If and only if two conditions holds. So first that the C of A mod the center of C of A is simple and topological simple. And moreover, actually this center is either trivial or it is the torus. And second, that this quotient UA mod C of A is again either trivial or equal to the torus.
Topological simple.
Yeah, there is no closed normal subgroup. I mean, in principle, there could be something which is normal subgroup and which is dense inside this, right? But it is not closed. Yeah.
So simple, just out of break.
This means that it has no proper close two-sided ideal.
Yeah, so it's also.
Yeah.
But,
What is the group?
okay, I see what the.
A- No, A is a algebra.
But you don't go these stuff, but that simple is also arbitrary. Right, so. Okay, just to add to.
So is this a generalization? I'm just trying to remember what the Elliott-Rodin result is. Is it along these lines or is it something else? Yeah.
Well, it's something. Yeah. Well, okay. So, yeah. So Elliott-Rodin proved for some special class of C-star algebras that if A is simple, then this is topologically simple. And Robert proved it for any unital C-star algebra that any unital C-star algebra, whenever this is whenever A is simple, then this group is simple. But the other direction is not true. So I mean the other direction to prove that A is simple, we need some more conditions, and in this case we need to assume also that A has at most one trace. And then we have.
Do you really need to assume it, or just the proof needs to assume it? I mean, do you have examples where?
No, we don't have an example. Yeah, we need it in the proof, but I mean.
Okay, I mean, it could still be true, right? Or
yeah, maybe.
That
But
without
I
the
don't-
trace condition.
Yeah.
Okay. Thanks.
Yeah, but still, I mean, there is this condition which is somehow, I mean, probably difficult to verify, and then we have one more characterization. We have some reformalization of this mirror property, which is used to, I mean, let's say to characterize C-star simplicity, for example, of reduced group C-star algebras. So we have something similar. We have some similar characterization of simplicity of A in terms of one parameter subgroups of U of A, but yeah, but because this is also one thing that I wanted to present, but because I was still not sure about some possible gaps in the proof yesterday and today. I will not mention it for now. Yeah, but this is okay. I wanted to present the proof, but yeah, but I was too slow, so I will just finish with the statement.
Very nice. Any questions?
In the audience.
Yeah. So this
else theorem. I mean, I find it a bit difficult to understand. I mean, I can see what it's saying, but it's difficult to contextualize, I suppose. So is the point that all of these ultimately consequences of this theorem, or rather the generalization that you prove?
Well, not really. I mean, for example, I mean, this result has had nothing to do with traces, and I mean, here certainly the traces are involved. So I mean, there are some new ideas, but of course, something from this is also used here, but let's say, but not everything.
Mm-hmm. Also, so there's this paper that I guess is covered by this result note, where I think Ping Wong Ng proves something along these lines. He's looking at the Jiangsu algebra specifically, which, it's simple unital, has a unique trace. And he's analyzing the structure of the unitary group. And I think he proves something like this, exactly like condition 1 here, that this quotient is simple, and then the center is the torus, I guess. I don't know if you're aware of this. I'm just saying, like, you seem to covering this paper quite a bit more.
Yeah, no, I'm not aware. Yeah.
All right, okay.
Yeah.
Question.
We actually don't know. So here, I mean, we have two possibilities, either trivial or the torus, but actually we are not aware of any case when it is actually the torus. I mean, all the cases that we know, it is with this assumption that there is at most one trace, then this quotient is trivial. But I mean, we cannot exclude this possibility in general.
Well, I'm making this remember, maybe it's just the center, or it's not. Well, I don't quite know.
Yeah, if the torus is in the center of C of A, then it means that the torus. I mean, this is the canonical torus. So if the canonical torus is inside C of A, then it disappears from the quotient. So then the quotient is trivial. So I mean, this can happen actually when this center is trivial, because the torus is not inside there.
There's a question from Anshu in the chat. What can you say about non-unital C-star algebras?
Yeah, I guess we can just work with minimal unitization, and yeah.
You want to ask your question?
Right, thank you. So first I wanted to say, I think the result of ping, I mean, was like somehow subsumed and generalized by what Robert and Chant did. I mean, I think it was like the first step, and then now Robert like did the whole thing, right? Like for every unit of simple C-star algebra, you get the structure of the unitary group. But I also want to say that somehow in this theorem, I guess like it will fail for commutative C-star algebras. I mean, or if you have too many one-dimensional representations, because right, the commutator subgroup of even the unitary group, I mean, we'll see nothing because
Yes.
right. So let's say maybe an assumption that one wants to put on is what you call perfect, or I mean, let's say having no one-dimensional representations, and then maybe that could work in general without the trace condition, right? Because otherwise, I mean, you're just modeling out too much.
I mean, of course, this this theorem doesn't work for unital C-star algebras. Sorry, for commutative C-star algebras, because they will be simple only if they are C, which I just for safety reasons excluded from here. So
Okay. Yeah.
yeah.
But I mean, the question, the conjecture or whatever, I mean, could still be that, you know, simplicity. I mean, I think after all, I think there are no examples where the C-star algebra is not determined by its unitary group. Is that correct? I mean, as far as I know.
Yes. There are C-star algebras which are. I mean, there are different C-star algebras with the same unitary groups. Yeah.
Okay. So there
on
is,
the other hand, also there is some class of C-star algebras for which, I mean, for which the unitary group is the relative invariant, which distinguishes.
it's an invariant. Okay, yeah. Right. I see. But it's
actually the case where they are the same is the commutative case. So for I think whenever you have two connected compact metrizable spaces, then the unitary groups of these C-star algebras of these spaces will be isomorphic.
I see. Okay, thanks.
Yeah, if you take any let's say compact connected metrizable space, and you take their C-star algebras, then they are different if the spaces are different, but the unitary groups will be the same. Yeah, because so the unitary groups in this case will be this, right? Continuous functions from X into the torus. Now I would have to think a bit for a while about the details, but somehow it boils down to this theorem that C of X and C of Y are isomorphic as Banach spaces, and these the connected component of the entity of this unitary group is just the Banach space quotient by some discrete subgroup, which is actually isomorphic to the to the fundamental group of this unitary group. Yeah, but I don't remember all the details, but these unitary groups are somehow very similar to these Banach spaces, and these Banach spaces are always isomorphic as Banach spaces.
I mean, topologically, the groups must be different, right? Like you could detect of the dimension basically by the dimension of X would be dimension of the.
No, I mean the dimension is not detected. I mean, if these X and Y are, let's say, if they are infinite, then the dimension is not detected. I mean, just from the Banach space structure. And these unitary groups are really just these Banach spaces quotient some discrete subgroup, which can be in some cases really simple. So these groups are almost always isomorphic for different spaces.
Right, if not, let's thank Michal again. And next week we have Jean Renaud coming, so stay tuned, or actually don't stay tuned, but just retune next week. All right, bye.
Thank you.